Yeah, dear participants, I am just waiting for a minute or two so that some more participants join. Professor Maiti is ready and waiting for my instruction. So as soon as I see that the number is sizable, I'll invite. Please join in time so that we can start in time and finish in time.
Okay, unmute your mic only.
Yeah. Can you hear me?
Yeah, I can
Yes,
hear
sir.
you now. Not through this. Yeah, now everything is fine.
Yeah.
I am keeping the phone. I am hanging the phone up.
Yeah, I am also putting the phone off.
Yes, Professor Maiti is back. He has come. There was a small problem, so it's over now. Sir, we have to open the presentation material.
Yeah, we are doing that.
Okay.
Yeah. Can you see?
Keep it full screen and then come into Google Meet. No.
Full screen. Google Meet, after Google Meet.
Material in full screen and then come to Meet, Google Meet.
Google Meet कुछ है?
Google Meet.
So we are there. You are presenting to everyone. So stop presenting. So what do? Next you are presenting.
Share the screen.
Now close this window. Sorry. Open the presentation.
Open the presentation. किधर है? It is presentation. Just a minute. How do you get that presentation? Can you see the screen? Can you see the screen?
We can see the Google Meet screen, sir.
Sir, now after keeping the application open in full screen, you have to then switch to the Meet session, and then there you have to go to presentation and the whole screen. That procedure we have to follow.
How do we do that? This screen तो है open कर दिया.
কি প্রবলেম হচ্ছে বলো?
Open Google Meet. Where is that? How do we get that Google Meet?
Your Google Meet is on. You are visible. Only
now
it is minimized. Maximize it. Just maximize it.
Maximize it.
Yeah. After that, you go to. You are already presenting. Yes, it is coming. Wait.
Okay. So what do we do now?
Just a minute. It is.
Now we are presenting. Stop presenting. No.
Yes, sir.
Okay.
Yeah. Now you minimize this Meet session. Minimize the Meet session.
Present now.
Present now.
Present now. Entire screen.
Okay,
Yeah.
do that.
Entire screen.
That he has done, sir. Kadre sir.
Yeah.
Now it's.
It's coming now.
Yeah.
Yes.
No, it is gone again. It is the same screen once again that was coming earlier.
Why it is happening?
But now we can see at least two windows. This PC and removable. Now it's fine.
Can
we can't see anything now on the screen?
No. Can you locate your file from one of those screens and double click it there?
My Skype किधर है? Where is Skype?
No. This PC one is about the PC.
Okay.
Another one is removable disk, E-drive. Maybe you have connected some pen drive.
Yeah, I'll get the presentation, right?
Yeah, I can see that. Double click and open it.
Yeah, it's open.
Yes, it is coming. Thank you. You can scroll down maybe.
Yeah.
Yes, sir. It is all clear now.
Yes, sir.
Yeah, thank you.
Sir, I request you to start your presentation now for the second
Yeah.
session.
Yeah, thank you. Yeah, so we'll get started back.
Right, sir.
Yeah. So you see that what we have, just I think this screen is fully visible and it's okay, readable.
Yes, sir. It is visible and readable. No problem. Like
Okay.
before.
Yeah, that's great. So
Yes, sir.
therefore, we'll get back. Sorry for the loss of time, quite a substantial amount of time we have lost. So we'll have to get back.
No
Yeah,
problem, sir.
yeah. So we ended by saying that for solving any stress analysis problem, we have to determine three functions, stress functions or stresses, sigma x, sigma y, and tau xy in two dimensions, each of which is a function of coordinates x and y. Alternatively, we have to make use of the two differential equations 6 and 7, which we have shown earlier. They are functions of each displacement. It involves the displacement u and v, and each of the displacement is a function of spatial coordinates x and y. Now you see that three stresses, sigma x, sigma y, tau xy, they satisfy the equilibrium equations. And if you remember, hello, Sachin.
Sir, if you don't mind that if it is not disturbing others, you can leave this close the background noise can be reduced slightly.
Okay, thank you.
Thank you.
Hey, hey. Sorry, is that okay now? Hello?
Sir, perfect. No problem. No problem. Perfect.
Yeah. So what I was saying that we had the two equilibrium equations that I have shown you earlier, that delta sigma x delta x plus delta tau yx delta y plus x equal to 0. If capital X is 0, let's think of that situation. Similarly, second equation is delta tau xy delta x plus delta sigma y delta y plus capital Y equal to 0, and if y equal to 0, we have these two equations involving two terms in each of the equations. Now, these stresses, they satisfy the two equilibrium equations. We have to determine the three stress functions. You know that one English mathematician, his name is J.R.E., he looked into these equations, then he came out that if we can define the stresses in terms of single function in the following form, this function is called ARE stress function. It's represented by phi. You can see that. And if we write sigma x equal to delta 2 phi delta y square, sigma y equal to delta 2 phi delta x square, tau xy is equal to minus delta 2 phi delta x delta y. So each of the stresses, they are given by second derivative of the stress function. Here is stress function phi. So if we write this, look at the sort of magic of this expression. So if you write that, what it turns out to be that irrespective of the form of this function phi, which happens to be a function of x and y, the two equilibrium equations are satisfied. See the two equilibrium equations, you see that one is this delta sigma x, delta tau xy, delta y equal to 0. So if we write the value of sigma x and tau xy in terms of this phi function, you see this equation, if you do that, if you substitute the value of sigma x and tau xy in this equation, you see it becomes 0 identically, irrespective of the form of phi. This equation is satisfied. Similarly, if we try to look into the second equation, second equation is what? That is actually delta tau xy delta x plus delta sigma y delta y equal to 0. If we put the value of again the stresses there, they are also satisfied. So therefore you see that this stress function has been so defined, it is satisfied. So it's an interesting thing that this stress function is so nice that it can satisfy both the equations identically, irrespective of the form of phi. Now, therefore, the question is, for any stress analysis problem, what remains to be done is that you simply determine this function phi, which happens to be a function of x and y, and you get the solution, provided of course, the stresses satisfy the specified boundary conditions. So you have some boundary loading on the body, and therefore this function must be such, it should be so selected that it satisfies the boundary conditions, and therefore you get the solution. The moment you have the function satisfying the equilibrium equations and also the specified loading conditions, you get the solution to your problem. That's the way it is. And therefore the question is that this stress function is such, its area stress function, it is such, it satisfies the two equilibrium equations, and therefore the question is we have to determine this phi function, single function. See, you had to determine three stress functions, sigma x, sigma y, tau xy. Now it has boiled down to that you simply determine phi as a function of xy such that it satisfies the specified loading conditions. That's it. And then, since its form is such, irrespective of the form of phi in terms of x and y, it satisfies the governing differential equation. So that's the. Now the question is, how do we determine phi? How do we go about? How do we get an equation involving determination of phi? You see, you remember that we had one equation which is compatibility equation. So if you remember that compatibility equation, this compatibility equation is this. It is nothing but delta 2 tau xy delta x delta y was nothing but delta sigma delta 2x square. This is sigma y plus delta 2 delta y square sigma x. So this is actually nothing but tau xy delta 2 tau xy is equal to delta 2 sigma y delta x square plus delta 2 sigma x delta x square. So therefore, if we substitute, this is the compatibility equation. So in this compatibility equation, if we write the value of all the stresses in terms of phi, then we get this equation. And this is the equation, you see. If we have to determine phi, this is the equation we have to solve for. One differential equation, it is fourth order differential equation that is to be solved for to solve any stress analysis problem. So therefore, if you have to find out the solution of any stress analysis problem, you have to determine phi as a function of x and y which satisfies this equation, plus it should satisfy the specified loading conditions at the boundary. This equation is known as biharmonic equation. It is nothing but actually delta to delta x square plus delta to delta y square whole square into phi equal to 0. This is called biharmonic equation. So therefore this biharmonic equation is the basis to solve for the stress analysis problem. And you see, solution using how do we find out phi? There are certain ways of going about it. Looking into this equation, you can see that you can write phi in some polynomial form like this. You can write phi ax square plus bxy cy square. So it's a symmetric polynomial, second degree polynomial in x and y. And you can see that if you try to write your sigma x is equal to delta 2 pi delta y square, if you do that, you see in this case it will become c. Sigma x is nothing but constant c. Everywhere it is c. Similarly, delta 2 phi delta x square, it is nothing but 2 into a. So it is actually some stress conditions. Similarly, if you try to write delta 2 minus delta 2 phi delta x delta y, it will become actually minus b. So this indicates, this stress function indicates some stress state in a body which is given by the value of the constants involved in this second order polynomial x and y. Similarly, if you try to write this polynomial in terms of this form ax cube plus bx square y plus cxy square plus dy cube, it also indicates actually a stress state. And you know, this value of constants involved a, b, c, d, it indicates the stress state. So therefore, you know, I just wanted to tell you that when you make use of the function in the form phi 1, then sigma x is equal to b, I'm sorry, c, sigma y equal to a, and tau xy is equal to b. So these are the actually stresses. And therefore, what is the stress? Boundary stress for a rectangular domain like this, it gives you a state like this on the boundary. Let's say this is in xy coordinate, a rectangular plate of dimensions. It is, let's say this is actually 2L and this is height is 2h. Then what it means, it gives a state wherein sigma x everywhere is c, sigma y everywhere is a, and tau xy is minus b. You know, it is actually minus b. It's depending on the value of b, it gives you the stress state. So therefore, this is it. Boundary stresses are like this. So therefore, the constant in the polynomial that indicates the state in the body, everywhere it is like this. Now I want to give you the polynomial which was given in the cubic form. You know, look at this. That the cubic form of the polynomial, you see, let us consider this. See this one, ax cube, bx square y, cxy square, dy cube. Now simply in this case, suppose we just simply take one term, we just consider a0, b equal to 0, c equal to 0, dy cube is the expression for phi. Then in that case, the stresses are given here. You see, for such cases, the stresses are given. Just 1 second. In this case, you see that phi is equal to dy cube, only one term. So in this case, what we find, sigma x is equal to d6 dy, y equal to 0, tau x equal to 0. So it's a case of stress state. You see what it means. If sigma y is 0, so if it is a rectangular plate of length 2L and height 2h, in this case what we find is that, see, this sigma x stress is varying with y and rest of the stresses are 0. So if we now consider the edge, let's say x edge at the distance L from the center, then the stress is varying linearly. See, if here x is constant, y is varying from bottom, let's say y equal to minus h here at the bottom and y equal to plus h at the top. then in that case, if D is positive, then you have that D is, when Y is H, then stress is 6dH. So highest stress is 6dH. At Y equal to 0, stress is 0. So it's a linear variation. Sigma X stress is varying linearly. And therefore, you see, similarly, the stress on the left-hand edge, it is varying linearly. It is actually tensile at Y equal to 0 and 6 dH at Y equal to H. So therefore, this is a case of simple bending. If you consider a rectangular plate subjected to bending, pure bending at the edges, then the stresses are given by this stress function phi equal to dy. So now the case is, what is this? This is the case of pure bending of a plate, where pure bending moment is applied at the edges. Here it is actually some moment is acting clockwise, and here some moment is acting anti-clockwise, and that's what is giving this stress linear variation. This simple bending stress variation in strength of material, it was done for. So that's the case. So the stress function for this case is given by Ty cube, where D is having a value which depends on the externally applied bending moment. We can determine that. See, we will determine this. What is the value of H? So, in this case, M is the moment, pure bending moment, M is applied. And now, if we try to consider that sigma X at a height Y equal to 8, it is 6dH. So if we want to take the moment which is externally applied, and if the stress is varying linearly, you see that then in that case, to get the moment at the edges, what you have to do is that sigma X multiplied by dy, and that's the sort of actually load there, and take the moment Y. So if you do the integration minus H to plus H, it gives you M is equal to 4dH cube. That's the moment. And therefore, you see that constant D is obtainable from this externally applied bending moment. So from this relation, if you finally write that sigma X is equal to 6 dy, and that is nothing but 3 by 2 M by H cube into Y. So M by I into Y. So you remember that simple bending stress due to bending moment on a rectangular plate is going to be M by I into Y. So therefore we have got the formula derived. So therefore the stress distribution, although we didn't go through this process, it was derived in the strength of materials from the deformation process. By the stress function approach, we get the same solution, and therefore the approach that we followed in strength of material, that gave the exact solution, and here we have shown you how to get it. And therefore you see that to find out the solution for problems which are given to you, you have to find out the stress functions in terms of X and Y, so that it satisfies the boundary conditions. That's what problem. So in the case of stress function approach, the beauty is that you have to simply determine a single function, and that single function should be so decided, its expression should be such that it satisfies the stress applied at the boundary of the body. That's what it is. So that is this Airy stress function approach. So just I wanted to give you some introduction to this Airy stress function approach. Now I just want to end by talking about the strain energy or potential energy, because you know potential energy. Yeah,
I have a question.
please.
So the rationale of the Airy stress function, if I repeat, is going to be actually phi is going to be, the stress function is going to be the assumed solution to the equilibrium equation. Can we say about it like that?
Say if you actually take a single polynomial in terms of x, y, whether it is 2 terms, 3 terms, that's your choice. Now the question is, any form of that stress function is going to satisfy the equilibrium equations, and the constants involved that you have to decide by seeing that boundary loading is satisfied by those constants. See, any form of the phi function, irrespective of its form, we have seen that it satisfies the two equilibrium equations because of the definition itself.
Yes.
But the question is, problem remains that solution to a problem, it involves finding out the stress function such that its form should be such that it satisfies the boundary loading. And that boundary loading is going to decide the constants involved in the expression that you have selected.
Yes, sir, I got it.
Am I clear? So I want to make it once more for the participants. You see, we have shown exactly that irrespective of form of phi, it could be anything involving x and y. But the question is, you must make sure that form that you have selected, it will have some arbitrary constants. Those constants should be such that it satisfies the boundary conditions specified. And this constant also should be such that it obviously that constant will actually make the satisfaction of the equilibrium equations, provided they have certain linkage, they have certain values. So that's what you know, that constants you must select. If you select that those constants actually making it to satisfy the equilibrium equation, but fact remains that stresses are ultimately going to be given in terms of those constants. Those constants will be such that it should satisfy that equilibrium equations will be satisfied, provided you know that you get delta sigma x plus delta tau xi delta y equal to 0. Similarly, delta sigma y delta y plus delta tau xi delta x equal to 0. So therefore the question is that you must select that those constants should not actually create any difficulty in actually satisfying those equilibrium equations. By any form it can be taken, but then you must make sure those constants are such that it is satisfying the equilibrium equation. That one part is done. But the question is, those constants are also going to give you the value of the stresses. Those stresses must be as per the specified boundary conditions. I think it is not becoming clear to participants as I can understand. See, the point is like this. Phi should have a form which, irrespective of the form of that function in terms of x and y, it will satisfy the equilibrium equations. But then those equilibrium equations, when you satisfy, you see that when you put the values, you will find that those constants that are involved, they will have some interlinkage. They will have some constraints on them. You know, they cannot be just arbitrary. They must be such that they must make those equations equal to 0. That is one aspect. Second aspect, that these constants must be such that the equations, the equilibrium equations are satisfied. Plus, at the same time, those constants are also going to be linked to the boundary loading, because the stresses are actually specified by boundary loading. So those boundary loading is going to be again derivative of that function, and therefore they are going to again have some linkage amongst them. So therefore, you know, these two, finally it means that you take a polynomial, it will satisfy the equilibrium equation, that is okay. But then question is, those arbitrary constants will be selected such that they are also satisfying the equilibrium equation. When you plug into them those equilibrium equations, if they are 0, they will always satisfy. But then if they have certain linkage between them, then it is going to be actually settled down. I think, let me explain this point. I think it's not become clear. Yeah, you see, yeah, that if we take phi 1, which is nothing but ax square plus bxy plus cy square. So if I take that phi 1, second degree polynomial, what we find is that, you see, here, this equation, once you try to take that form, this form, and try to take its second derivative, my equilibrium equation is what? It is nothing but 4 times derivative of phi with respect to x. If you take 4 times derivative of this function with respect to x, it will be 0. Similarly, if you take 4 times derivative of this function, 2 times with respect to x, 2 times with respect to y, irrespective of a, b, c, it will be satisfied. Similarly, if you take 4 times derivative of this expression with respect to y, irrespective of value of a, b, c, it will be satisfied. So in that case, if we, it's a polynomial which is actually satisfied irrespective of the value of x and y. So that one part is done. But the fact remains, when you try to see for this expression of phi, stress in the y direction is delta 2 phi 1 delta x square. So it will be actually, you see, if you try to take that, it is just 2a. So stress in the x direction is 2a. Then similarly, if you try to take the y stress delta 2 phi delta, delta 2 phi delta x square is 2a, which is nothing but sigma y. Similarly, delta 2 phi delta y square, which is sigma x, which is 2c, and delta 2 phi minus delta 2 phi delta x delta y, it is nothing but actually minus b. So therefore, in this case, you see, this phi is satisfying equilibrium equations irrespective of the value of a, b, c. But your external stresses are dependent on these constants. So therefore, in this case, you have the simple problem of satisfying the boundary conditions, setting these constants a, b, c properly. Suppose you go to the next one. Next one, in this case, you see, we have taken this one term only, dy cube. In this case, you see that the d cannot be arbitrary. If you just put this value in the differential equation, it will be satisfied. But then, when you try to calculate, in this case, you see, if you take 4 times derivative of these terms in terms of x, it is going to be, irrespective of value of a, b, c, d, it is going to be satisfied. Similarly, if you try to take the 4 times derivative of this expression with respect to y, it is going to be satisfied 0. Similarly, if you try to take the 4 times derivative of p x square y, c or x y square, it is going to be all 0. So therefore, it's satisfied. But then, when you try to take the stresses, in that case, you see, you have to settle the constants a, b, c, d, such that boundary stress conditions is satisfied. So this is another situation. Similarly, in this case, phi 3, you will find that in this case, a, b, c, d, e, all of them have to be satisfied or selected so that it satisfies the equilibrium. All these constants are to be selected. And at the same time, these constants to be selected considering the boundary condition. So therefore, the problem has become different now. The polynomial is going to be satisfied by the differential equations provided these constants are properly selected. That's it. So you have the function, but then the constants involved are to be selected. That depends on the boundary condition. So therefore, that's much easier. So this is the type of problem. So Sachin, I think I'll have to stop here on this point and then get moving. Is that okay?
Yes, sir. That's fine. That's fine.
Okay. Thank you.
Thank you. Thank you.
Next, potential energy. See, potential energy, because this finite element analysis, it makes use of the potential energy for getting the equations involved in the formulation. So therefore, the potential energy, what is that potential energy? Potential energy for a body which is loaded, its potential energy is defined by strain energy and also the work done by external forces. So strain energy, what is the strain energy? Strain energy of deformation. So therefore, let me explain to you strain energy. What is strain energy? If a element is subjected to sigma x stress, then in that case, you see the strain energy involved because of the sigma x is nothing but half sigma x into delta y into t, that's the force, and the extension, let's say in the x direction is delta x. So therefore, this is actually strain energy of the body. So it's half sigma x into delta y into t multiplied by deformation is epsilon x into delta x. So that's the deformation. So therefore, it becomes strain energy due to sigma x is half sigma x epsilon x, and volume of the element is delta x delta y into t. So that's the actually potential energy due to sigma x stress. Similarly, due to sigma y stress, we have the stress, the force is sigma y into delta x into t, and because of this stress, the strain is going to be epsilon x, epsilon y. So epsilon y into delta y, that will give us displacement. So therefore, the strain energy to sigma y is half sigma y epsilon y into delta. Similarly, for stress at tau xy, what is that? You see, if a element is actually subjected to this, its form becomes like this. It becomes actually a rhombus, like you see, that rhombus. So herein, the vertical edge has rotated towards x direction by gamma xy by 2. So that's the rotation of the vertical edge. Rotation of the horizontal edge is also by some, the strain is actually gamma xy by 2. So these are the angles of deformation. So therefore, the strain energy due to this is calculated by half tau xy into gamma xy into delta. So finally, the strain energy in the element is going to be nothing but delta S is half sigma x into epsilon x plus sigma y into epsilon y tau xy into gamma xy multiplied by the volume limit. So those total strain energy in the body. So if we have a body of given area or volume, then in that case, total strain energy is given by delta S into volume integration. So therefore, that's the strain energy of the whole body. It is represented by S. Similarly, the work done by external forces, think of a case that you have a body wherein the loads acting at the boundary at point 1 is P1x, P1y, then second point is P2x, P2y, and it goes on, number of points will have force in the at that node in the x and y direction. Therefore, the work done by the external forces, if we say that at the point 1 on the boundary, the displacement in the x direction is u1, displacement in the y direction is v1, and it goes on up to pnx, pny, where n are the number of nodes. Then in that case, the total work done by the external loads are actually nothing but half u1 p1x, v1 p1y, and it goes up to nth node un pnx, vn pny. So that's the actually work done by the external forces. And if we write in a matrix form, it is going to be total displacement vector transpose of that multiplied by p. So it is in matrix form half u transpose p. So that's how we can write in short form using the matrices. So therefore, the strain energy is integration of delta S over volume, and work done by the external forces W is nothing but half u transpose p transpose. So this is the work done by external forces. And therefore, you see the potential energy of a body pi, which is defined by strain energy minus the work done by the external force. So please remember this. This is very important, that strain energy of deformation is given by strain energy of the body U, and work done by the external forces is given by W, and the potential energy, the energy which is available after we release the loads, that is going to be given by strain energy minus work done by the external force. This is the potential energy, and it's very important. You must remember that potential energy of deformation of a body is represented by pi, and it is nothing but volume integration of the product, this one over the volume of the body, minus the work done by the external forces, which is nothing but boundary displacement transpose multiplied by boundary loads acting. So this is what is important. So therefore, that's potential energy. We'll make use of these relations often in the finite element formulations. So therefore, to close this section that I started in the afternoon, I think I'm sorry the participant must have found it little difficult, because I had to introduce to you certain and sort of meaning some airy stress function approach without having some practice and solving it yourself, and on my writing it on the blackboard, it will be little difficult to appreciate. But to summarize, I said that you can find out solution to a stress analysis problem analytically, and the problem is that you determine the stress function which involves constants, arbitrary constants, and these constants have to be so selected that it should satisfy the equilibrium equations, two equilibrium equations, and at the same time boundary loading conditions. That's the crux of the whole problem. And if you take recourse to any of the book on theory of elasticity by Timoshenko, like, you will find like lots of examples giving answer to problems using airy stress function approach. Then we introduce the potential and strain energy of deformation. So strain energy of deformation, which is nothing but product of stresses and strain, and that is to be half into product of stress multiplied by strain, and that expression is to be integrated over the volume of the body so as to get the total strain. And finally, potential energy, which we generally talk potential energy. Potential energy is nothing but strain energy of deformation minus the work done by the external forces. And therefore, that's the potential energy which I have explained at the end. Now I'll move into my second part or second lecture on, rather next lecture on finite element. So therefore, I think now we'll find it little easier to appreciate, and it is more of physics than mathematics. Thus, unfortunately, if you are having exposure to matrix algebra, it is much easier. Otherwise, I'll have to give you more explanation. That's the problem that we have. Anyway, let's come down to finite element analysis. So finally, what stress analysis means? It means that you have been given a body whose geometry is given, and you have to find out the displacements at every point of the body under the specified boundary conditions, or you have to find out the free stresses in terms of the boundary loading. So that's the problem. And we also came down to the conclusion that if we work in terms of displacements, then you see that we have to find out two displacements at every point of the body. If we want to work in terms of stresses, we have to find out three stresses at every point of the body. Now let's see. I just want you to think for a moment that suppose this is the body. So this is the body, rectangular body, simple geometry, and its boundary loading is specified, and loading can be non-uniform all over the boundary. And I would like to now also come down to the point that this problem of stress analysis is equivalent to finding out the UV displacements at every point of the body. And those UV displacements must be available at every point of the body. Thereby, we can get the strain at every point of the body, because strains are defined in terms of first derivative of the displacements, and then stresses are given in terms of strains. So therefore, you see, every problem is solved. So if we now try to see that for a rectangular plate of this type, if we just assume that we'll try to look into the deformation. Suppose this is the body, that is the plate which we were showing as ABCD. So this is the plate, and you see the central figure. So that's the plate which is ABCD. It was actually rectangular. Now suppose I plot the displacement at every point of the body in this ABCD. I show it in the XY plane. So this is X direction, horizontal direction, and the other direction, which is in the Y direction, is look into that 2 directions, X and Y. And now, if I plot the displacement at every point of this body in the vertical direction, which is indicated here as U, please now concentrate on the figure. So I am plotting X in this direction, Y in this direction, and displacement u in the vertical direction. So if I now plot the vertical displacements at every point of this body ABCD, and then you see u, if I plot, I get a surface, that hatched surface. You see, it's a Samiana. Think of it as a Samiana, which is indicated by that doubly curved surface A, B, that is actually that Samiana, which is hatched. So that's the Samiana shape of the surface. So if I want to determine u variation over this domain ABCD, I have to find out the equation of this surface in terms of x and y. Is that clear to everybody? So problem of finding out the in stress distribution, what we need to find out is to find out this u surface, which is shown by that hatched surface. Is that clear to everybody? Is it?
Yes.
Yeah.
Yes, sir.
Yes, sir.
Yeah, thank you so much. So therefore, we have to find out this surface. And you say it's a function of x and y. So now look at the some considerations. Now this domain ABCD, which is shown in the middle figure, I break it into 8 triangles. Look at this. I just actually AB, then CD is there in the vertical direction, or rather CD is the top edge, and I break this domain, rectangular domain, into small triangles. Look at this, equal triangles. So if I look into the surface above an element like, let's say, element 1, which is at the left bottom, A2, 3, that's the element. And if I look into the surface of that, above that triangular element A2, 3, you see that surface looks like this. On the most right hand picture, you see, I have drawn that element A2, 3, and you see surface is there. That U3 over that element is just this one. This is a small surface, a part of the Samiana. And if you see now, if you just shrink the size of this element, make it small and small, it will become a small patch of that surface. It will look like a triangular tile. It's a flat tile. Is that clear to everybody? As I shrink the size of this element A to 3, you see its size, the surface size will become small and it will look like a flat tile. It will not doubly curved. That size is so very small, it will look like a flat tile. So that's it. You see, as you reduce the size of the element, it looks like a plane surface. Then in that case, if you have such elements in the domain, 8 such elements, the whole surface will look like an assemblage of 8 flat tiles. Please note this. So if I make the size of these elements very small, so then in that case, you see, surface which is doubly curved, originally it looks like a small flat tile. So therefore, these surfaces will look like small tiles if the element size reduces. At this point, we can talk alternatively. Above these elements, we have actually patch of the surface which is triangular, which are doubly curved, but then we can approximate them by flat tiles. So these triangular tile which are doubly curved, if I just approximate it, it will become like actually flat tiles, small flat tiles. So therefore we can approximate this doubly curved surface by a plane surface, it's a flat tile. So therefore if we want to do that, so above that element which is nth element, n equal to 1, that flat tile equation can be written very easily. I can write very easily. You see that? That's the point I was saying, that above that element n, the doubly curved surface can be approximate as a flat tile. Flat tile, and its equation, we can write it u equal to alpha 1x plus alpha 2, alpha 1 plus alpha 2x plus alpha 3y. Repeat, that above that element n, which is having vertices as 1, 2, 3, it has 3 nodes. This surface originally is doubly curved, but I can approximate it as a triangular tile, a flat tile of triangular shape, and its equation is then going to be given by u equal to alpha 1 plus alpha 2x alpha 3y. So it's a function of x, a linear function of x and y. That doubly curved surface, which is square tile or cubic tile or square tile, or actually square in polynomial, but then now I can approximate it as a flat tile, and its equation is alpha 1 plus alpha 2x alpha 3y. This alpha 1, alpha 2, alpha 3 are called generalized coordinates. Generalized coordinates. And now how can I determine this? Since this surface is given by u equal to alpha 1 plus alpha 2 x plus alpha 3y, it must satisfy the value of displacement at the 3 corner nodes. So if I represent the displacement at the 3 corner nodes as u1, u2, u3, then in that case I can solve for these constants alpha 1 to alpha 3 in terms of the triangular, the vertices of the triangles, and therefore finally on simplification, substitution of the value of the generalized coordinates alpha 1 to alpha 3 in equation 1 will get u equal to n1 plus u1 plus n2 equal plus n2 into u2 plus n3 into u3. So this is actually the displacement of any arbitrary point within the element or on the boundary is given in terms of the 3 corner node displacements. That's the simplification that we have got. So the displacement, that surface which was approximated by a plain triangular tile, its equation is n1 u1 plus n2 u2 and n3 u3. And n1, n2, n3, they are called shape functions, and the value of these shape functions are given in terms of alpha 1, alpha 2, alpha 3, and it is given explicitly in the following presentations. You see, this is how it is. This displacement shape functions n1, n2, n3 are given here. See, n1 is nothing but ai plus bix plus ciy by 2 delta. I varies from 1 to 3, 1 to 3. So we get n1 for I equal to 1, n2 for I equal to 2, n3 for I equal to. Just 1 second.
Yes, sir, your battery is low.
Yeah, so that's what now I have charged it.
Yeah, no, thank you.
Yeah, that's what it is.
Okay.
So you see that in 1, it gives you the value of n1 and n2 and n3 for I varying from 1 to 3. And these ai, bi, ci and delta, they are constants. And look at this. This a1 is given in terms of the corner node coordinates of the 3 nodes. a1, a2, a3 is given in the first column. b1, b2, b3 is given in the second column. c1, c2, c3 is given in the third column. Please, I just want you to spend 1 minute in this slide. You see that these constants, n constants involve a, b, c, and then you see that or constants b1, b2, b3. What is b1? It is nothing but coordinate of node 2 minus coordinate of node 3, y coordinate, y2 minus y3. b2, y3 minus y1. b3, y1 minus y2. Similarly, c1 is x3 minus x2, c2, x1 minus x3, c3, x2 minus x1, and this a1 is given again x2, y3 minus x3, y2, a2 is x3, y1 minus x1, y3, a3, x1, y2 minus x2, y1. And delta is the area of the triangle 1, 2, 3, that triangular element, its area. So that's how we see that finally we have been able to give the displacement as a function of the 3 nodal displacements. You see, this expression is extremely important. this expression has enabled us to define the displacement at any point on the boundary and the interior of the element in terms of the three corner node displacement N1, N2, N3. And this is possible by using the shape functions N1, N2, N3, and N1, N2, N3 are dependent on the coordinates of the nodes and also function of x and y. So N1, N2, N3 are functions of position plus the coordinates of the nodes. And thereby we have got the displacement at any node in terms of the three corner node displacements. This is what the simplification, this is possible by discretizing the domain into small elements. Similarly, if we follow the procedure for V, so V surface will also be a doubly curved surface, and that doubly curved surface again can be approximated, and we can finally write, following the similar approach that we just followed for U, we will find that we can write V at any point within the element and also on the boundary of the element in terms of alpha 4 plus alpha 5x plus alpha 6y, a polynomial, linear polynomial or plain tile-like, and by proceeding as above, we can determine the this generalized coordinates alpha 4, alpha 5, alpha 6 in terms of the three corner node displacements. Look at here, that finally here also V at any point within the element is given by N1 multiplied by V1 displacement of the node 1, N2 multiplied by V2 displacement of the node 2, N3 multiplied by V3 displacement, Y displacement of node 3. So therefore, you see, it is again given in terms of similar polynomial, and these N1, N2, N3 are having the same expression as in the case of U, and that's what is given here. Finally, combining the relations, that we have got this this relation 2 and 5, if I combine this relation, or rather 2 and 6, if I combine the relation 2 and relation 6, it will look like this. Displacement at any point, UV displacement of any point UV is nothing but this matrix, which is of dimensions 2 rows, 6 columns, multiplied by the displacement of the corner nodes, which is shown here. That N matrix multiplied by this displacement matrix. So that's what is the displacement UV at any point is given in terms of the corner node displacement U1, V1, U2, V2, and U3, V3. This is important equation. This is node displacement matrix of dimensions 2 by 1, 2 rows and 1 column, and this N matrix is a matrix of 2 by 6, 2 rows and 6 columns, and displacement UN, which involves actually 3 U displacement and 3 V displacement, which is of size 6 by 1. So therefore we have got the displacements in terms of at any point in terms of the corner node displacement. So it is shown there. Up to this point, is it clear or it is becoming difficult? Participants, could you please express, are you getting it easy or difficult? Any
It's
comment?
looking okay, sir.
Yeah?
I think it's looking okay.
Yeah. So if they have any questions, any doubt, let them raise.
Yes, no problem. I have already told them.
Yeah, if I just give 1 minute, 2 minutes, if they want to ask some clarifications at this point.
Okay.
Participants,
please, if you have any questions, you can ask the questions now so that sir can go ahead.
No?
Looks okay, sir.
Okay. So I think please just think of it. Again, I want to just summarize what I have done in this segment. You know that we are talking about stress analysis. And finally problem boils down to determination of stresses, three stresses at every point. Alternatively, we have to determine the displacements at every point of the domain under the specified loading conditions or boundary conditions. So therefore, what I then talked about, if I try to plot the displacements, let's say over the whole domain, let's say I plot the displacement in the vertical direction at every point of the domain. So if it is a rectangular domain, then you see you are going to get a surface which will look like a Samiana. In the case of you also, you will have a surface which is going to have shape like a Samiana if it is actually plane, if it is actually what you call that curved surface, it can have simple form like a Samiana. And this could be having actually very complex shape. It could be, wobbly and all that, but then in some cases it can be just curved surface, plain curved surface. So that's the surface we have to determine. And it's a function of x and y. But suppose you try to just think of it, it's a rectangular plate and then you break it into number of small triangles. And if you look into the surface, just above that small triangle, that portion of the Samiana will like a curved surface, small curved surface. And if you, that is a doubly curved surface, it's going to be a function of x and y, so it's a doubly curved surface. But if you want to approximate, by a plane surface, it will look like a triangular tile. So you just think of it, if you have number of triangular elements, then each of the surface will look like a triangular tile. And they will be actually having continued, they will have actually same straight line stitching between them, and it will look like a flat tiles, triangular tiles stitched at the boundary. So that's the total surface. And we want to determine this surface, whole surface. Approximately the problem is to determine those triangular tiles equation for determining that surface approximately. Each of the tiles will look like a plane tile and therefore its equation will look like simple in form like alpha 1x plus alpha 2y plus alpha 3, alpha 1 plus alpha 2x alpha plus alpha 3y. Similarly, V will look alpha 5 plus alpha 4 plus alpha 5x plus alpha 6y. So you see, you have to determine these generalized coordinates alpha 1 to alpha 3, alpha 4 to alpha 6, and we have shown that it can be easily determined in terms of the displacement at the corner. So height of the tile edges at the three corners. So that's what finally, and finally therefore we find that if you want to determine the whole surface, it is determining those triangular tile equation, and finally it is determining the displacement at the corners, and then we get the surface, full surface, and that's what the finite element approximation gives rise to. So finally the whole surface determination involves determining the corner node displacements only subjected to the boundary loading conditions. So that's what has been possible. Just a minute, why it is gone?
Sir, you can just follow the same path that you usually follow for opening your notes in your computer.
Just a minute.
The presentation is on. That's not a problem.
I know. How do I get that? I just hit somewhere.
Or is it open at the bottom? Is it open at the bottom? The Acrobat thing at the bottom? No, this is Zoom Meet. Close this.
Yeah, this one Zoom, huh?
Yeah, this is not required. I see an icon there. I think it is there. Acrobat Reader, that red icon at the bottom. First. Yeah, that one.
Yeah, okay. Yeah.
Yes.
It's okay. It's okay? It's
Yes,
okay?
sir, fine, perfect.
Okay.
Perfect.
So, yeah, great. So therefore, you see that finally, what we have got is that determination of the displacements at all the nodes is the problem. And now you see that if we have been able to determine the surface over each of the elements, then your strains, how is the strains? Say strains are simply, this is very easy. You see that you want to determine strains is delta u delta x. So therefore it is nothing but derivative of these shape functions with respect to x multiplied by the 3 corner node displacements in the x direction, epsilon y derivative of the v function with respect to y, which is nothing but shape function derivative multiplied by the corner node displacement v1, v2, v3. So epsilon y is obtained in terms of the corner node displacements. Similarly, gamma xy, shear strain, which is delta u delta y plus delta v delta x, which is given by delta n1 delta y, delta n1 delta x, and it goes up to delta n3 delta x multiplied by these 3 corner node displacements u1 v1, u2 v2, u3 v3. So this is what again is strains are given in terms of the corner node displacements. So finally what happens once we have been able to determine these functions, or if we have been able to determine the corner node displacements of all the nodes, then you see you get the strains at any point within the body in terms of the corner node displacements by these equations. And it finally, this derivative of the shape functions, it is actually written in a simple form. This B matrix, it is called strain displacement matrix, B matrix multiplied by corner node displacements. So strain displacement matrix is given by B matrix multiplied by corner node displacement matrix. Then stress-strain relations we have just now got, we can now get stresses in terms of displacement. Sigma x, sigma y, tau xy is equal to D stress strain matrix multiplied by strains. And if we substitute the value of D, finally what we get, that this D is given, D matrix is given on the plane stress at the top, on the plane strain at the bottom, and therefore your stresses are going to be here. Stresses are given, combining these, you see, sigma stress, sigma x, sigma y, tau xy is nothing but D into epsilon, which is nothing but D, and epsilon is nothing but B multiplied by U. So therefore, this is the stress displacement matrix. So therefore, here, you see, again you get the stresses in terms of the corner node displacements. That's the beauty of these steps, that once you have approximated the required surface in terms of plane tiles, it's very simple that your problem is to just determine, your problem of determining the displacement surface is nothing but determining the displacements of the corner node under the approximation of linear variation of displacement within the element, and you get this simplification that stresses are given by the stress matrix, stress strain matrix multiplied by B matrix multiplied by U. So that's what is the position. So I think this is what is going to be okay for today, and I want to again to actually rebrush the portion, and then we'll take up the remaining portion easily, and that will be much clearer and it can be presented faster. So let me just actually go ahead. I'll stop taking any further thing, but I would like to again actually go over the portion that I talked about finite element today. Please, I want all of you please to concentrate again so that you don't have any doubt. And if you have any doubt, please ask me at any point you require. So I started here. What I did, I simply talked about that finite element problem in terms of stresses. One has to determine the stresses at every point of the domain in terms of three stresses. Alternatively, we can say that it is problem of determining the displacements at every point of the domain subject to the specified boundary conditions, which can involve loading and fixity conditions. It can be fixed at a point, can be loaded at some point. No, these are the boundary conditions. So we now just concentrate on the determination of displacements at every point of the domain. So if you want to talk about this problem, you have the loading, you see that there is some variation of the loading on the top face, source of variation of loading in the y direction over the bottom face, and then on the right side you have shear loading acting, on the left face also shear loading acting. They have some magnitude. And finally the body is undergoing deformation, and if we try to just plot the deformation, take the body in the xy plane, which is a horizontal plane consisting of the area, and then try to plot the displacement at every point in the x direction in the vertical direction. So if you do that, you get a surface. That surface may look complicated. In some cases, it may look like a doubly curved surface. It's just a sagged Samiana or inflated Samiana, that sort of surface, doubly curved surface. So if we want to determine the displacement at every point of the domain, we want to find out that sagging or inflation or actually elevation of every point of the Samiana. So we want to determine that. So now we took up the simple case, that let us try to look into the case of simple case so that we can understand easily. So we took up the case that that domain is rectangular, and we just take the body in ABCD in the XY plane, and then in the vertical direction we plot the U displacement. So if it is just actually Samiana which is inflated, like, so you see that if you are lucky, you might get a surface like this. It's a doubly curved surface. It has some curvature in the y direction, some curvature in the x direction, but at every point you have some elevation. So this surface equation is a function of x and y, which can involve x, x square, xy, y square, and so on. But then this surface, if we try to just consider a portion of the surface above a single element, we have divided into 8 elements, and if we just try to consider an element which is at the bottom left hand corner, that element is vertex A or node 1, then node 2, node 3. This is the triangular element. Its number is 1, n is equal to 1. So that surface, if I just concentrate that portion of the surface which is doubly hatched in the left figure, and on the right figure we have just segregated that portion of the surface above the element n equal to 1 or 1 to 3. Look at that, that's this surface. It's a small patch of Samiana. It's doubly curved. Now, this doubly curved surface, I can approximate it. I can approximate it by the elevation. Just if I think of a triangular tile which is joining the vertices U1, U2, U3, then this will look like a triangular tile. So it becomes a plane approximation. I can take it to be approximation of higher order, that's possible, but then to make it very simple, we just keep it like a plane triangular tile. And if it is a plane triangular tile, it's a plane equation of a plane in xy coordinates. I can write it that u is the vertical coordinate. U can be written as u equal to alpha 1 on constant plus alpha 2x plus alpha 1. So this is the general expression we can write in terms of the 3 corner node displacements. And this expression, that doubly cut surface is approximated by a triangular tile whose equation is alpha 1 plus alpha 2x plus alpha 3y. How do I get these generalized coordinates? Since this equation is valid for all the points within the element and on the boundary, therefore, this equation is also valid at the node 1, 2, 3. At 1, 2, 3, elevation of the surface is u1, u2, u3. So therefore, you see, by substituting the value u1 is equal to alpha 1 plus alpha 2 x1 plus alpha 3 y1, u2 is equal to alpha 1 plus alpha 2 x2 plus alpha 3 y2, u3 is equal to alpha 1 plus alpha 2 x3 plus alpha 3 y3. So these three equations, because it's valid at the three corner nodes. So if I have that, I have three equations to solve for three unknowns, alpha 1 to alpha 3, and this alpha 1 to alpha 3, if we solve and if we write in a short form, it's going to be nothing but u equal to n1 u1 plus n2 plus n2 u2 plus n3 u3. This displacement at any point u in the x direction is given in terms of three corner displacement u1, u2, u3. And these constants n1 into n3, these are functions of x and y, and its form is explicitly given here. You see, these functions are given in this form n1 ai plus pix plus ciy by 2 delta. It's a linear function. So you find that these constants are dependent. It has three sets of value, I equal to 1 to 3, and these values are given here. A1 3 values, B1 3 values, C1 3 values in terms of the corner node coordinates. So we have been able to get finally the displacement at any point within the element and on its boundary in terms of the three corner node displacements. It's very important thing that your surface equation, that surface above an element is given in terms of the three corner node displacements, and it involves for any point the value depends on the xy value of that point. So that's how the linearization gave rise to. And if I follow the similar principle in the case of y displacement, I can take the V surface again. It will be again doubly curved. It will have form involving x and y. And if I just make it into a plane form, then its equation can be written as alpha 4 plus alpha 5x plus alpha 6y. These are again constants which can be determined from the fact that this equation is valid at the three corner nodes. So it should therefore satisfy value at node 1 V1, value at node 2 V2, and value at node 3 V3. And thereby we will get three equations to solve for the generalized coordinates alpha 4, alpha 5, and alpha 6. And finally, you see that we get the total form of V N1 V1 plus N2 V2 N3 V3. Again, we find that Ni has the same form as in the case of X or rather U, and you see these constants are again these arbitrary constants A1 to C, AI to Ci, AI, Bi, Ci. 9 constants are also given in the form of the nodal coordinates. Finally, combining these UV expressions, we get displacement at any point within the element and on its boundary is given in terms of the corner node displacements U's and V's. This is what final expression that we have got. And that's what is very important, that this finite element analysis, it helps you in approximating the shape of the surface in terms of simple surfaces, and those expressions help him to write the displacement surface over the whole body in terms of the displacement at the corner nodes that you have constructed in the domain. That's what it is. So this is discretization process that helps in the finite element analysis. It helps you to determine, therefore determination of the whole U surface and V surface of the whole body is equivalent to determining just the displacement at the corner nodes that you have constructed by discretizing. So that's the starting point of the finite element analysis. So I think we'll stop here today. We'll start again from this point. Please try to reverse whatever we have discussed today so that you can appreciate the later part of the finite element formulation. And you might have find little difficulty because we are trying to talk about a lot of symbolism here and matrix algebra, but nevertheless it's very simple mathematics, nothing difficult. Once you look into the derivation that I have handed out to you or that is available on the PPTs, you will be able to understand them. Thank you very much. Any questions?
Sir,
Yeah.
sir, alternatively, if somebody tried to write the equations in terms of finding out the stress, I mean attempting to finding out stress, will it become stress-based formulation of finite element method?
Right, that is what it is. That is what. But you see, that stress-based finite element formulation is difficult, and it is not easily understood because there are physics will be lost, and that's why that is actually the, you see, hybrid formulation. What is this formulation is called displacement-based finite element formulation, approximation based on displacement form of the surface. And if it is stress-based formulation, then it is going to be stress approximation, which is much more difficult to understand. That's why that is difficult. And we'll come to that. You see, stress-based formulation is difficult to understand. And then you have hybrid formulation where both displacement and stress assumed formulation can be there. Assumed displacement based, assumed stress based. These are the two different formulations. But somebody can have assumption of displacement surface and also stress surface together. That is hybrid formulation.
Yes, sir. Okay. Thank you very much.
Thank you. So we'll close it for today.
Yes, sir. Yes, sir. We'll close it for today, and we are meeting in your next session tomorrow morning at 9:30 a.m.
Okay. So,
Yes, sir.
fantastic. No problem.
Yes.
So
Thank you very
that
much for your time.
So that is actually what? That is first session of the day or second session of the day?
No, it's going to be the first session of the day.
So it is 9 o'clock.
9:30.
Okay. Thank you.
Yes. Thank you very
We'll
much, sir.
start. Thank you.
Yes.
Thank you all participants. Please try to reverse and then have questions. Think of it, and whatever difficulty you face, please read it tomorrow so that I'll be happy to explain to you. Then move forward.
Thank you, sir. Bye.
Thank you, sir.
Thank you.
Thank you so much.
Thank you so much.
Dear participants, we will meet tomorrow morning at sharp 9:20 a.m. Please log in so that the session can be started at right time at 9:30 a.m. Tomorrow's remaining discussion is going to be equally interesting, and if we give Professor Maiti full 1.5 hours in that session, I'm sure all of us are going to immensely benefit from the discussion. So I request you to join tomorrow with equal interest at 9:20 a.m. for the meeting, and I'll invite Professor Maiti to join the meeting at 9:30. Thank you very much. Have a nice day.
Thank you.